Okay, this is a quick video about motivating the moment of inertia. Why do we use this formula? Different books will start in different places. Some books will derive the moment of inertia starting from torque, some will do it from energy, some start with angular momentum. And so, what I want to do is just really quickly motivate it with all three. One of the things that you might notice is that, look, F equals ma, Ke equals a half mv squared, and P equals mv. And you just say, oh, well, these are the rotational versions. And okay, that is true. V becomes omega, and okay, maybe M becomes I. It doesn't explain at all why I is as weird as it is. I will show you how to calculate I in a different video, but in this video, I just want to focus on explaining where that weird formula comes from. And I'll do it all three ways: torque, energy, and angular momentum. So first from energy, if I have a ball and the ball is moving to the right, then that ball has kinetic energy, and we can just write a half mv squared. But of course, you know that the ball is actually made up of multiple pieces, and each of those pieces has kinetic energy. And really, what I ought to be doing is adding up the kinetic energy of all the different pieces. And in this case, since they're all moving the same speed, really the only sum I have to do is over the masses. And if I sum up all the masses, I just recover the total mass times v squared. There's not really much to talk about in this case. On the other hand, if I allow my ball to rotate about the z-axis, in other words, the ball is going to rotate in this direction. There are other kinds of rotation that create a bit more of a headache. We're not going to worry about those in this video. But if I rotate about that axis, then they can't possibly have the same speed anymore. The reason is this guy travels this arc, and this guy travels this arc. They move different distances in the same time. They must have different speeds. And that creates a bit of a headache because now I have to kind of incorporate the speeds in order to get the total kinetic energy. On the other hand, what I do know is that all of them move the same angle. They all go pi over 2. And what that means is that they all have the exact same angular speed. And each velocity is distance times angular speed. And so what I can do is, if I get rid of the VI in favor of an R omega, well, look, okay, now I've got an R sub I there, but the omega doesn't have an I on it because they all have the same I. This allows me to reorganize things and write the ugly sum as I. And so that is the origin of I. It's just a way of reorganizing how we choose to write things. So that's energy. And you might say, well, okay, that's a ball. It's really nice. I could take any object I want. I could make a weird little object like that. And so long as I have a normal rotation about the z-axis, I'm still, at the end of the day, just making little circular arcs, and everything I've said is still true. Okay? So what about if I change the axis I'm rotating about? If I, for example, rotated about some different axis B, so now I have B, I'm still creating circular arcs as I rotate it about B. In other words, this also helps explain why an object has different moment of inertias about different axes. In other words, moment of inertia is not really a property of the object, it's a property of the axis. And so we have to be very careful when we calculate moment of inertia. So that's energy. For torque, I basically make the exact same argument, only now, look, in order to get this thing spinning, I have to accelerate each of these pieces. If it starts at rest, I have to accelerate each of these pieces. And so how do I accelerate the pieces? I exert a force on them. Now, this is really weird because at the end of the day, maybe I push the sphere here, but that push doesn't actually touch R2. That push touches this piece here, and this piece pushes on its neighbor, and it pushes on its neighbor until eventually, somehow a weird version of that push gets to each one of the pieces of the sphere. Those internal forces are extremely complicated, and in some sense, the moment of inertia tells you how the sphere decides to spread out all of its internal forces. For algebra, though, all we really need to consider is, just like we replaced V with omega R, now I'm just going to replace A with alpha R. And so if I make that substitution, now I have the torques. I have R1, F1. This becomes R1, M1 times A1T. And if I make this substitution, look, here's this term again. Each one of my pieces has some torque exerted on it, okay? And I can write that in terms of alpha, which is the same for all of them. And so, of course, if I add up all the torques on all the pieces of my object, then I'm going to end up with this same sum again, which of course I call I. One thing to keep in mind is if I add up all of the torques on each of the little pieces, you might wonder, well, wait a minute, what is that equal to? Do I have to worry about all those internal torques? Actually, it turns out you don't have to, because all of those internal torques are between pairs of objects. So here's my lever arm, and whatever the torque on this guy is, it's caused by the object on the right pushing on it. But it exerts an equal and opposite force on the object on the left, and they both have the same lever arm. So that means that if I sum over all the torques, internal torques, they'll cancel, just like internal forces cancel. So that actually means that if the sum of the internal torques is 0, I can actually just say that I alpha is the sum of external torques. And that's normally quoted as Newton's second law for rotations. Okay, and then finally, angular momentum. It's basically the same argument, only now I'm going to talk about the linear momentum of each piece. Okay, and so the first piece has a momentum that depends on its radius and its volume. I'm just going to do the exact same trick I did last time. In other words, I'm going to add up all of the angular momentum, and when I trade out V equal R sub I times omega, I end up with this term again, and so you end up with I omega. So this is why I is what it is, and I will show you how to calculate it in a different video. Okay, hopefully this was more helpful than confusing.